That was an insane journey, honestly. Holy shit. I learned so much about networking, about asynchronous programming, about all of this stuff. It's actually fucking insane. And I think my journey is finally over. I think my journey is finally over, and soon I'll be able to fully rewrite the server part of Coil in C3. Hello everyone, and welcome to yet another recreational programming session with Mr. Zozin as usual. So today is an offline session, so there will be no chat or anything like that. We're going to continue developing our coroutines library, and just to recap, what is coroutines? Coroutines are sort of like a lightweight threads which execute, all of them execute on a single operating system thread, or even quite often on a single CPU. Right, so they look like this. So let me find some examples in here. So here is the example of a counter. We have a single coroutine in here, which accepts basically the upper boundary and simply counts from 0 to that upper boundary, printing its own ID and the counter. And we create two of such coroutines. And the thing about coroutines is that you manually actually switch between them. Right, so there's an operation called yield, and it calls to the scheduler, and it switches to the next coroutine, which allows to sort of like interleave them. Right, so we can actually take a look at how that looks like if I just rebuild all of the examples and stuff like that. So it's going to be build coroutine, and as you can see, so we have 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and we're sort of like interleaved between these coroutines. So in the example, we're actually starting two coroutines. One is shorter than another, right? So one counts from 0 to 5, another one counts from 0 to 10. And this is intentional, so because I want the first coroutine die and a longer coroutine to continue executing, just to test how that works. And this is basically the result, right? So we have two different IDs, then the shorter coroutine dies and the longer one continues counting until it is done. So in fact, there's three coroutines in here. There's also main coroutine, which constantly yields basically switching to the counter coroutines until the amount of alive coroutines becomes equal to 1, which is the main coroutine, and then everything is finished and cleaned up. Right. So the question is like, why would you even use such coroutines, right? Because you have threads. You can just create two threads and that will work for you. The thing about threads is that as soon as you start using them, you need to think about synchronization, right? So you are starting to have thread safety problems, which means that you need to introduce mutexes and stuff like that. If you're doing coroutines, everything is kind of a deterministic and everything is executed on a single thread, so you don't have to think about synchronization that much. In fact, you can send information from one coroutine to another one through a global variable, and that's fine. That's totally fine. So it simplifies synchronization between them and coordination. So it's not really for parallelism, it's more for concurrency. But at the same time, you're only utilizing a single core, right? So you kind of lose in performance. Well, this is useful when you actually don't do much work on your threads, especially if you're doing asynchronous networking. So these kind of coroutines are perfect for asynchronous networking when majority of the time you're just waiting on I/O, right? You're waiting on a read operation or write operation and stuff like that. So creating a lot of threads for this kind of stuff is kind of like a wasteful. It would be better to just like create these lightweight sort of fibers. I think in some libraries and some operating systems, these kind of threads are called fibers. So, and we can even demonstrate that. We even have an example which implements an echo server, right? So here it is. So it's a very simple example. What are we doing here is that actually this is C3. So here we had C, right? So, and here we switched already to a completely different language, which is C3. Right, if you never heard about C3, I recommend to check it out. So here's the website. Not the best language I've ever tried, but it's an alright language, right? It's also in progress, so some of the things may not work, so be cautious when you're using this language. I'm a trained professional. I kind of got used to using unfinished buggy software, so it's totally fine for me. So, and the cool thing is that this language has a very convenient socket interface out of the box, so creating this kind of echo server is very easy. So what I can do in here, I can listen to host and port, right? So just a random host and port, I mean local host. So then I can set it to non-blocking. Right, and essentially now in a loop, I can try to accept a connection, and if I didn't receive any connection, I can actually yield to other coroutines. And other coroutines are already accepted clients that just listen to incoming data, right? So for example, there is a read loop, right, that checks, is there something to read? If there's nothing to read, we yield to another client, which also will check if there's something to read in there and yield to another one, and so on and so forth. As soon as we get some data, we're initiating the write loop, which tries to write things, and if it couldn't write, it yields to another coroutine, and so on and so forth. So the idea in here is that the coroutines try to do an operation, and if the operation is not available yet, we just yield to another coroutine, right? So we just go and do something else, right? So these kind of things are perfect for these situations when you did some work, now you try an operation, and operation is not available yet. Well, I guess I can go do something else. Right, this is kind of perfect. So we can even test if this works. Let me see if I can just do echo. Right, so here you go. So we're listening to localhost 6969. I can just use Telnet to actually connect to this entire thing. So the client has connected, so I can say hello. And as you can see, the server can see that we received 7 bytes, and here is hello. We received hello back. And now we can actually connect another client, right? So we can say world in here, and we again received 7 bytes. Maybe we can actually send more, and there we go. So we can also close this entire stuff. Everything is working, everything seems to be twerking. But the problem here is that it busy loops, right? So I can even take a look at the BTOP. So let me see. So there should be one thread that is currently busy looping. There's actually 2 of them. I don't really see. Ah, that's bizarre. Nothing is really busy looping. But it's like there's 2 cores 50-50 in here. But even that is kind of a meh. That should not happen. This is because, again, we keep basically trying an operation and we keep yielding. So what we should do instead, we should do the thing that we did in our previous sessions, specifically the session about select poll and epoll. Before we started to explore coroutines, we were actually working on a futures library. Futures is also kind of an asynchronous primitive, and it's completely different asynchronous primitive. And we already implemented this kind of stuff for the futures, right? So an ability to basically, if the operation, read or write operation is not available on the socket, go sleep and don't spin on that. We already implemented that for this library. So what I want to do now, I want to implement the same thing for the coroutines library. And I think it's going to be kind of similar. It shouldn't be that hard. In fact, we can even reuse some of the code from this library in a coroutines library. So that's going to be basically the topic for today's session. Sounds good? Sounds Gucci? Tamaguchi? Let's freaking go. So how are we going to be doing all of that? This is a very, very interesting question. I suppose we are going to literally create like operations. Maybe something like, instead of this entire loop, we're going to have coroutine read, which is going to accept maybe the buffer that we're trying to read. So here we're reading the buffer, right? So we're going to just accept the buffer, and it's going to potentially return an error. It probably never going to return would block, because this operation is supposed to make sure that the read operation is available. So we're not going to expect would block in here. Because of that, I think it makes sense to just like unwrap this entire thing and just expect n, right? So this is the kind of operation we want in here. And that operation should basically replace this entire stuff, right? This entire loop. Instead of spinning, we just have this one single operation. If that operation is not available yet, the entire coroutine is basically sleeping, right? We're not even switching to that coroutine yet. So the scheduler should be kind of aware of this kind of thing. And by the way, I suppose we have to maybe provide the socket from which we're reading this entire thing. So, but this is a TCP socket, if I'm not mistaken, right? So this is a TCP socket. Maybe I have to explicitly say that this has to be read TCP socket. So I have an idea that the coroutine library that is implemented, basically the C3 part of the coroutine library, is going to have some nice wrappers that can work with C3 primitives like TCP sockets and stuff like that. And this is going to be one of them. It's not going to be part of the C library, but it's going to be sort of like an additional thing that C3 bindings provide on top of the C library. So I'm going to explain what it means a little bit later as we get into that. So after that, we also want to have an operation that just writes the stuff back instead of this entire loop, right? So instead of this entire loop, it just writes it back. And how we're going to be doing all of that. So it's probably going to be coroutine write TCP socket. So it's going to be client sock. And we need to actually write the buffer from 0 to n. Actually, it's not from 0 to n. It's starting from 0 and n bytes, right? So that's what we're doing in here. And what we're gonna get in here, in fact, is how much we manage to write. So we may not write the entirety of the buffer in here. So that's something that may happen. So that means we need to repeat this operation several times until the buffer is exhausted. And another thing that I forgot to check in here, I think, is that if n happened to be equal to 0, right, even if the operation was successful, but the n was 0, so we didn't read anything, that means the socket is basically closed. So we want to break out of the outer loop, something like that. That's what we want to do. So, and in here, we need to actually write things sort of like in chunks. Because of that, I think we need to employ the trick with the chunk in here, right? So this is what we need to employ in here, I suppose. Maybe I'm gonna just go ahead and move this chunk somewhere here. Right, so here is the chunk. Maybe I'm gonna even do it here. So it's essentially buffer starting from 0 and n bytes. So this is the chunk. What we're gonna be doing in here, we're gonna be writing the chunk. Right, we're writing the chunk if we only wrote 0, so that means the socket is closed. There's no point in actually working with this socket anymore. And we need to now do that in a loop, right? So while chunk length is greater than 0, we keep doing this kind of stuff. And then once we manage to write a little bit of that chunk, we actually advance in the chunk. So basically actually starting the chunk from M up until the end of the chunk like this. So that's about it, I think. So that's about it. So instead of all of this complicated looping and stuff like that, we're going to actually have much simpler thing like so, hopefully. Yeah. So read TCP socket, read n bytes, then take a chunk, and then write it back to the client. So much simpler. And it actually looks like a synchronous code, but in reality, it's asynchronous. So within this call, I would expect the scheduler to actually just like make a decision whether to yield to another coroutine or to put the coroutine to sleep and so on and so forth. Right now, this kind of stuff doesn't even exist, right? So I completely confabulated this code. It's non-existent yet. So let's try to compile this entire thing, right, and see how it's going to fail. Right, so it's going to complain about this specific function. I think there's no point in compiling all of the examples. We probably need to compile only the echo, right? So it's going to build the echo. Let's build this entire thing. And what is it complaining about? So read TCP socket is not available. Let's go to the coroutine C3. So here is the low-level operations that interface with the C library. But we're going to have things like a read, usize read TCP socket, read TCP socket, and write TCP socket, and they're going to be implemented in C3, but they're going to be calling to maybe lower level operations that are written in C at some point. So in here, we're going to accept TCP socket itself, right? So this is going to be socket, and the buffer that we're trying to write. And then in here, the same is going to happen for the write. For the read and for the write. All right, so that's pretty cool. So what's going to be the low-level operation? That's a very interesting question. I suppose the low-level operation is going to be maybe even just like an integer, right? So because the error is going to be reported through a negative value of some sort. And it's going to be just a read. So, and in here, we're going to accept the file descriptor pointed to the buffer and the size of the buffer. So just n. So this is the read operation, a low-level read operation, and low-level write operation. So, but their actual name in C is going to have a prefix of coroutine, right? So it's going to be coroutine read and coroutine write. Maybe I should actually call them, so what the fuck did I do here? Maybe I should actually call them something like receive and send to sort of emphasize that these are sockets. So we can even take a look at the names of these separations in here. So yeah, so here is the send and receive, but send and receive also accept additional flags. I'm not sure if we're going to be exposing these flags. Maybe we'll do. We'll see. We'll see. So, but for now, let's actually keep it read and write. Okay, that's pretty cool. Let me think now. Let me think. I need to know the internal structure of TCP socket. So let's actually take a look at that. So it's going to be OPT C3. So it's somewhere net TCP. So TCP socket, it's internally just a socket. Okay, so let's take a look at the socket. So it has a native socket, and within the native socket, I think native socket is defined as a file descriptor. I don't remember how exactly it is defined. So let me see. I can always just grab the whole thing just to see its definition. I think it is defined through equals. Right, here it is. So it is in line, which is FD. There's so much hierarchy. It's like this entire language is written by a Java developer. Why there's so many freaking wrappers? I don't know. Anyway, so what we need to do in here? So we need to take socket and sock, and since it's a FD, which is probably an integer, we can now call to maybe read FD. So buffer, we do have a pointer to the buffer, and we do have the buffer size. So in this entire thing, we'll probably return an integer, right? So which is probably n, unless it is negative, right? So if n is negative, I think we should be able to somehow get an error somehow. I don't really know. I don't really remember how you do that. So I think it's OS error no or something. So let me see how it is done usually. Maybe it's a socket error. Yeah, I kind of vaguely remember this. There was an operation called socket error. Let me actually find this operation. So here it is. It's a socket error, and yeah, it basically it takes libc error no and converts it to a socket error. Maybe we can use that literally. Maybe we can use that. Let me quickly try to do that. So OS socket error, and we just rethrow the whole thing. Not really rethrow, we can just like return it like this if it is negative. Right, because I'm pretty sure if read will fail for whatever reason, it will set error no, because underneath it's going to be calling something from the libc. So I think it is a valid thing to do something like that in here. I think it is valid. All right, so in a similar thing we're going to do for write operation in here. So this is going to be just write. And that's about it. So this is how I see these simple wrappers. So the only thing we need to do now is to just implement these operations in C. All right, so let's actually try to compile this entire stuff and see if it's going to fail with the linker. Right, so it doesn't know about TCP sockets, that's understandable. So we need to probably import some stuff. Let's import std net. I think it also has to be TCP. Yeah, there we go. So now it complains about undefined reference, blah, blah, blah. Classic, freaking classic. So coroutine.h, so here is where we define the API in C. So let me actually put some stuff in here. So we're going to have coroutine read, which accepts file descriptor, pointer to the buffer, and the size of the buffer. There you go. So this is what we're going to have in here. I'm not going to document it right now. I'm going to probably document it a little bit later. So this is going to be right. I think here maybe I have to say that this thing is constant, right? But I'm not 100% sure. Just in case, because usually the write operation in C, in pure C, this is a wrong one. So let me take a look at this one. So it does have the buffer constant, just in case. So that kind of makes sense, I suppose. But anyway, now I'm going to go to the coroutine. So we're lowering down to pure C. So here it is. And I suppose in here we can just throw some sort of an assert, right? Or maybe it would be better to do something like error to do coroutine read. So this thing is not implemented yet, but we're also going to abort. So, and this one is going to be coroutine write. There we go. So let's try to recompile this entire thing and see if it's compiling. Right, so it doesn't have, surprisingly, it doesn't have, you know, IO. So let's include the IO. So it complains about some unused things. That's understandable as well. So let's put this kind of stuff in here. And for the write, we're also going to put this kind of stuff. Okay, everything seems to be compiling. It's probably not going to work, right? So we can just try to run echo server, right? So yeah, so for now we only fail on a read and write operation. So that means we need to connect first, and there you go. So here is the coroutine read. It would be kind of cool if it also tell me where exactly it failed. So we can do something like, I don't know. So SD, so this one is going to be file, this one is going to be line, and let's just freaking do that. So where is that? So I'm going to grab this entire thingy-majingy. I think my laptop is spinning right now. This is because this thing is working, or is it? I'm not sure. I don't think anything is spinning right now. Spinny. Nah, it's just an effect of the previous run, so everything seems to be fine. Okay, so what I need to do in here is just like I need to rebuild everything just in case. Maybe I can do that in several threads. All right, so I can connect that, and look at that, it is failing precisely in the place where we expect it to fail. So we just need to implement this thing. Isn't that a poggers, my dear friend? I think it is freaking poggers. So yeah, this is where we're gonna be maybe putting the things to sleep, sort of speak. How do we keep track of the coroutines? In fact, how do coroutines even work? All right, so in the global scope of C, we have so-called contexts, which is array, which is a dynamic array of context. And a context is just a pointer to the top of the stack of the coroutine. So the way we can actually have several coroutines is that we have separate stacks, and yield, what yield does, it simply switches between the stacks. So simulating the simultaneous execution of these things, or at least interleaving their instructions. And in fact, when you call yield, you actually jump in straight into the assembly. Right, straight into the assembly. And in that assembly, we just push in the state of the program, all of the necessary registers, right? So the registers that survive the call of the function according to the Linux x86-64 ABI, right? So we're just saving all of that on the stack. Then we are taking the top of the stack and we're passing it as the argument, and we just call into the C function, which takes care of actually switching the context, right? So that's what it does, right? So it's switching the context. So yeah, but the thing is when the coroutine finishes execution, right? So when the coroutine finishes execution, this is the function that we jump to, right? And the way we sort of like remove coroutine from the scheduler is very simple and very straightforward. So we have basically a bunch of coroutines in the array. So here they are. So we have 5 coroutines in the array. So when we have maybe some additional memory pre-allocated after that buffer, right? And so what we do, we look at the coroutine that we want to remove. We want to remove this coroutine, and we swapping it with the last one in the array, right? We're swapping it with the last one in the array, and then we decrement the count of the array by 1. So we don't really care about the order of the elements. Because of that, we can actually remove the element in O of 1 by basically swapping it with the last element and then just decrementing the count. So that kind of works. But that also invalidates the IDs, right? That also invalidates the IDs, because we use ID as an ID, we use just an index of the coroutine. So, and this is kind of a bug that we created to fix later. And what's funny is that when we create the coroutine, we allocate the stack with the malloc. And as of right now, we're just letting the stack leak because we can't remove the stack in here. We can't literally do that. So here's the current context. I can't just say stack base and just free it in here because we're currently executing on this stack. Right, so essentially by doing something like that, we're pulling the rug from under ourselves. And this, I think it's kind of a dangerous operation. So I just like let it leak a little bit, you know, let it leak, let it leak. Let it leak, let it leak. So how I was thinking we approach that? So I think instead of trying to free all of the stacks, what we have to do, we have to reuse them, right? So essentially, instead of removing the coroutines from the array, let's actually mark them as dead, right? It is dead. Because of that, the IDs are not going to be invalidated. So the IDs are not invalidated. And furthermore, like when we create a new coroutine, we can actually not add the coroutine at the end of this dynamic array, but actually find the hole in that array and put the new coroutine in here, like this. So and also reuse the stack that we pre-allocated in dynamic memory. But here's the interesting thing. We create a problem that now adding a coroutine is not O of one operation, because like before, if you want to add a new coroutine, you just append it at the end of the array and it's going to be O of one. Well, not really O of one, O of one amortized, because we're having dynamic array, which resizes every time you ran out of capacity, but on average, it acts like O of one anyway, right? So, but actually it's amortized. So we can't really add a new element to this array in O of one. So we need to have kind of a different strategy in here. So that actually prompts us to implement a very simple allocator for the coroutines. Essentially, we need to have, I suppose, 3 arrays now. 3 arrays. So the first array, I suppose, is going to be the pool of the contexts that actually allocates all of the context, like contains all of the allocated context and all of the allocated stacks and so on and so forth. Right, so I'm going to denote them with dots. Right, and on top of that, I think they also need to have some sort of like a flag that indicates whether they're already taken or not. Let's call them dead or not. So by default, it is dead. That means it's not used. And this is how we're going to distinguish them. And essentially, another array that we're going to have in here is the active coroutines, right? So let's call them active. And those things are not going to be the context. They're going to be literally indices. It's an array of indices within the pool. Right, it's an array of indices within the pool. So essentially, how we're gonna work with all of that. So originally, pool is empty. So what we do, we allocate a new element in the pool, right? We allocate new element in the pool, and we add its index to the array of active. So then we want to allocate another one, right? So we pre-allocate another element in here, and we add that index to here. Okay, that's cool. So let's actually add a bunch of them. Right, so now we have 3 of them, and here are the indices. And when we are switching the current context, we're actually switching not the index within the pool, but the index within these indices, right? So we're sort of like circling with these indices. So now, if we want to remove this element, right, if we want to remove this element, we're removing it with O of 1 with the trick of swapping it with the last element, right, and then decrementing it. But on top of that, we also marking this as dead, right? We're also marking this as dead. And here we need to introduce a third array, the third array that keeps track of the holes that we created by deallocating elements from the middle of the pool. Right, so this is the dead hole, so to speak. So this is 1. Right, so and now the next time you want to allocate a new coroutine, instead of appending it to the pool, you first look, do we have any dead indices in here? Okay, so we have one dead index, so that means I'm going to take that one, mark it as alive again, without appending a new thing to the pool, and append it to the active ones. Right, and now if I want to add another one, I look, do we have any dead? Okay, so all of the deads were taken, so let's allocate a new element in here, and there we go, here's the new index, right? And we're circling only within these indices. So this is a simple allocator where all of the operations, allocating a new element, deallocating a new element, are all O of one, or at least O of one amortized, right? So because we're dealing with dynamic arrays in here. So this is what I think we need to implement in here to maintain O of oneness, right? Constantness of the operations. And I think that's what needs to be done in here, and that will allow us to even reuse all of these like pre-allocated stacks and stuff like that. I think it's a good idea. I really like that. So that should basically kill these two birds with one stone, right? Just implement this sort of allocator. I don't even know, does this kind of allocator have any name? Because this is the allocator which I kind of discovered myself. Right, so this is allocator, more or less efficient allocator for objects of the same size. Right, so we have objects of the same size which are contexts for the coroutines, right? And we just like efficiently allocating them. Like allocation is O of one, deallocation is also O of one, right? So the main difficulty with allocators is implementing like a general purpose allocator that can work with objects of different size. When all of the objects you're allocating are of the same size, it is extremely easy, right? It is extremely easy because you can just keep track of the holes of the same size and just like reuse all of these holes. But if you have holes of different size, that's where the problem comes in. In fact, I think I explored this kind of problem in my implementing my own malloc video, didn't I? I think I did, right? So it's a very old video actually. I didn't expect that I'm going to be referring to that video in 2025. Tsoding, what is it called? Malloc. There we go. Yeah, writing my own malloc. Look at that young boy. All right, so I'm going to be putting that in a description for all of you guys. There we go. So now, let's freaking go. Let's freaking implement all of that stuff. I think it's going to be interesting. I haven't implemented this kind of allocator in quite some time. So should be fun. Contexts. So here is the context. So, and we need to keep track of the indices. Right. So I suppose let's literally call this dynamic array indices. So, and the elements that we're going to have in here are going to be size t's. Items. Right. So in here we're going to have a count and we're going to have a capacity. And we're gonna have two indices array. So indices is going to be active, right? So this is active, and the second array is going to be dead. Both of them are indices. Very cool. Both of them are indices, and all of them are first initialized with a 0. Maybe we can even do a little bit of a align by regex. Boom! Can your ring do that? Okay, so I'm sorry. Like I don't even have a chat in here, I'm still acting like a clown. Okay, so we need to go to coroutine. Coroutine go. Okay, go. First thing we need to do. Oh, this one is interesting. So we have, yeah. So we have some cool stuff in here, but that's for later. Maybe if for completely different session. We'll see. So if we want to allocate the new thing, we first need to check, do we have any deads? Right, so if, so dead, was it, did I really call it? Yeah, I did call it dead. Did count greater than 0, so that means we do have some deads. Okay, so we're gonna actually popping them out from the end. So I'm going to take count -1, obviously -1, dead items like this. And this is the index that we want to have it here. So I'm going to call it ID, right? So this is the ID. So I'm looking up that context, that ID within the context, right? So this is what we have in here. And I'm basically marking this thing as not dead. One of the things I suppose would be nice to do is to assert, just in case, that this thing is in fact dead, right? So just a sanity check. So if it is in a dead array, it's also dead. So we say that it's not dead anymore. Pretty cool. So it is not dead anymore. and I suppose we need to do the usual thing. It's going to, like, it's stack based. Its stack base is already initialized properly. Its RSP might be a bit wacky. I think its RSP might be a bit wacky, but I'm not 100% sure. But maybe it doesn't even matter. Right, so what we want to do in here, I suppose, is, yeah, just take its stack base like this. Just take its stack base, add stack capacity, and take its RSP, and do the usual thing of just like pre-populating the state into which we're going to be returning. Right. So the thing in here, I already explained that in the previous streams. I really recommend to watch the previous stream, actually entirety of the coroutine playlist, right, because it explains the whole lore of this entire thing. But essentially, when you're allocating coroutine, you have this sort of like stack. This is the region of memory. But the thing about the stack is that it grows from right to left, not from left to right. So that means the top of the stack starts to grow in here. And when you push something on the stack, it grows like this. So, but also on the top of the stack, we have to store the state of the coroutine, all of the registers, and I suppose some functions to return to, and so on and so forth, the RAP and whatever. And this is what we're doing here, right? So here is the stack base where the stack begins from the left. So we add stack capacity to that. Right, and then we basically fabricate the initial state of the coroutine. So when you actually yield to this coroutine, it's gonna restore to that coroutine and start executing. So that's basically what we're doing, right? So, and I even put the comments in here, just like push a value of the register onto the stack, but in reality, you're just like writing 64-bit integer into the array memory. So that's basically what's going on in here, basically. Okay, so and after that, we used to just append that thing to the context, but we don't really have to do that anymore because it's already there. It's already there. Stack base is immutable. We don't really change it. The only thing we have to do in here is to just set its RSP like this. So this becomes RSP, and there you go. We just reused the whole thing, which is kind of cool, I think. Which is unfathomably based. So, but on top of that, we have to decrement the amount of deads. So one of the things we can do is essentially first decrement the dead, and then reuse this entire thing. So after decrementing, it's going to be -1. So yeah, that's a good one. So you can simultaneously decrement the array and get the last element. So that's pretty cool. That's pretty cool. And after that, we just like return out of this thing. So otherwise, if you don't have any deads, you have to allocate completely new thing. That's what you have to do. You have to allocate a completely new thing. And this is what we're doing here. And we can just leave it as it is already, I presume. We can just leave it as it is. In fact, so we'll also have to make modifications to how we yield. And honestly, we should not access context items directly, just like this context directly. So what I think I'm going to do, I'm going to also change the name of this global variable. So it will break in all of the places I try to use it, so I can go through all of the places and modify them, right? So a little bit of a compiler assisted refactoring. So look, there's a little bit of a code duplication in here, and that just means that we have to kind of compress that. We definitely need to compress this entire stuff. So what I'm thinking we need to do, when we allocate a new thing, we should not append it to the context at the end. We should append it to the beginning and kind of pretend that this entire thing already exists, right? So here we already taken an existing thing, and here we're adding a new existing thing. So maybe we can even append a completely empty one. So then later I can do something like context items and take the last one. It's not actually this one, it's like -1 stack base. In fact, I think what I need to do, I need to share the ID variable between these two branches, right? So I need to set maybe ID to something not initialized yet, right? It is not initialized yet. And in here, I'm taking this ID from the debts, right? So I'm taking this ID from the debts, but in here, what I'm doing is that I'm actually taking this ID as the last one in the context that I just appended, that I just pushed in here. So that actually enables me to use this ID in here and pre-allocate this entire step. And look at that. Look at that. This is really fascinating. So these two chunks of codes are actually equivalent. They are actually kind of equivalent, so but there is missing this line, but yeah, it should be there. So that means I can actually take this entire chunk of code and literally just factor it out outside of both of these branches, like this. So I think that is a good approach. I do think so. Yeah, so we have ID, and depending on whether you have some dead slots or not, that ID is going to be set to different things, right? So we have some dead, you take it from the dead. Let's make sure that it's dead and so on and so forth. Let's mark it as not dead anymore. So if you don't have any dead, we create a new one and we set that the ID to that one, but we also allocate the stack base. And then it's the same thing, right? So we are reusing the same chunk of code for both of these kind of situations. In fact, this code doesn't even care anymore like where it got that ID from. It really doesn't care. Furthermore, maybe coroutine go should also return that ID. So, and then by that ID, the client may even, you know, look up some additional information about the routine and stuff like that. You can even check whether the routine is dead or alive by the ID or something. That's a lot of interesting things, but I don't want to actually mess with the API yet because it will break the existing, you know, code and stuff like that. So I just want to, you know, modify the way we allocate things. All right, so that sounds pretty cool. I really like where it's all going. Let's fucking go. So that kills two to-dos with one stone. So reuse the stack for new coroutines. That's exactly what we're going to be doing by removing elements. Yeah, so like none of that is a problem anymore. Right? The code is not compilable yet, but I think we can already safely remove those to-dos, right? So because we made modifications that kind of move towards fixing both of these to-dos, right? I really like where it's going. Okay, so let's actually try to rebuild that. And what do we have in here? Boolean doesn't know about Boolean. God fucking damn it, mate. So let's do bool. All right, so what else do we have in here? Okay, so, and this is precisely why I put underscore in switch, right? So because now current is supposed to point not in the context, but at the indices. So in fact, that kind of means that the current should be outside in here, right? So it basically points at the current active thing. Can I realign some of this stuff like this? Is that a good idea to actually mark all of these things as static, right? Because I don't think it's going to be, they're going to be available outside of the this library, right? So yeah, let's actually mark them as static. Anyways. So now I'm going to try to go through all of that stuff. Okay, so what do we do? We take current, right, and the current actually points at active. So we have active items current, and that's an index within the contexts, right? So we have like, you know, a little bit of like a double indirection in here. So first we look up who's the current active. We take its ID, and then we take this thing in here. All right, so, and essentially we save our RSP that we received from the caller, that we received from the yield to that specific thing. Okay, so after that, I suppose what I have to do, I have to do this, increment the current, but also I have to wrap it around, and I'm wrapping it around not by the amount of context, but by the amount of actives. There you go. So that's how we do that. And after that, I restore the next active context. So I have to do this kind of thing again. Right, but since the current was modified, right, it's not going to be necessarily the same. Right, and all of the context, let me query replace contexts, again the contexts with underscore. There we go. All right, so current, oh, okay, so it's double R. What else do we have in here? So when we are, okay, this one is interesting. Initialization is creating the first coroutine. That's what it is. And yeah, it has to be, I think what we have to do in here is also di append active as 0. Right, so because the coroutine with the index 0 is the first one, it is the main coroutine, it's the main procedure. To be fair, in here I would like to maybe assert some things. For example, that the context count is equal to 0, context active is also equal to 0, and stuff like that. I'm not really sure, actually. Not really sure. So we're gonna rely on programmer not calling this thing twice. I think I even have a to-do to allow programmer calling it twice, and just basically, yeah, so initialize the coroutine runtime must be called before using any other functions of this API. After the initialization, the currently running code is considered the main coroutine with the ID equals 0, should not be called twice. And I have a to-do, allow calling it twice, because why not? Yeah, so I think it's gonna be separate to-do. Basically check that this thing was already called once, and just allow it to call. Just exit if it was already called, right? So what's wrong with calling it twice? I mean, so if the programmer does a fucky wacky, why not just allow programmer to do fucky wacky and not fail? Because we can detect that. Anyways, so let's go through the rest of the compilation here. So context is undeclared. Oh, it's underscore. Yeah, I forgot. Right. Next one, finish. Oh, this is when we actually removing the coroutine. This one is fun. Broskis, this one is fun. So here is the thing. When you call a coroutine with the ID 0, we basically kill and deinitialize all of the coroutines, like all of them, completely. So that's what's interesting in here, chat. That's what's interesting in here. And how we can do that? I suppose we probably want to, first of all, free all of the stacks. And this is where freeing the stacks is actually safe, because ID 0 means we're executing on the original organic thread that was created by the operating system. Not allocated with malloc, but created by the operating system. So if we basically remove everything starting from the index 1, not from the index 0, but from the index 1, and just free each individual stack, we're not going to be pulling the rug from under ourselves. So I'm going to take contexts, actually count, right? So plus I. And yeah, so it's going to be contexts underscore items, I, stack base, and we're just freeing all of these things. So freeing the stack of the context with the index 0 is dangerous because it was never malloced, right? So it doesn't need to be you know, freed. So after that, we can just like empty out all of these stacks, right? So we're emptying out all of this, not really stacks, but arrays, right? So it's going to be active also becomes 0, and dead also becomes 0. But I feel like what I want you to do is that when you call coroutine finish in the main thread, it stops and initializes everything like you never called init ever. Which means that probably what I want to do in here, I want to actually free all of the arrays allocated by all of these dynamic arrays, right? So by all of these items and stuff. Actually, underscore has to be somewhere here. So that's what we want to do. This is going to be active items and then dead. And after that, I think I want to mem set all of these things to 0. So then you can actually call coroutine init again, initialize the environment again. Right, as I want to have an opportunity to just like completely switch off the magical coroutine runtime like you never called it before. Right, I think there should be an opportunity, like an ability to do that. Contexts. So I think it's fair. Active and dead. So we're doing all of the initialization here. So deallocating all of the stacks and then deallocating all the memory by dynamic arrays and so on and so forth. Right, but if you call finish not in the main coroutine, we only remove that specific coroutine without deallocating any of the memory, because we're going to be reusing that memory. So I think it's a pretty good design, in my opinion. Just saying. Right, what else do we have in here? So memset. You don't have memset, really? So let's just include the string. So what else do we have in here? So context underscore. Okay, so this is where we have to now remove the current coroutine, the currently running coroutine. How are we going to be doing all of that? So all of this code is kind of like meh. It should not exist anymore, I think. So we need to take a look at the current, right? So we take the active items current, right? So active items current, and we are looking it up in the contexts. Right, so underscore active, looking it up in the context. So what we have to do in here, we have to mark this entire thing as dead. We're marking it as dead. After that, we di appending that thing to the dead. So current becomes dead. So that's what's going on. Current becomes dead. And now we also need to remove this entire thing from active. Right, that's what we need to do. We need to remove it from active. And we're going to be doing the same trick of swapping between these two things and just like, you know, reducing the count. So in active, I'm going to do temporary variable. So active items current, right, I'm taking that. Then since I saved the current, I can replace it with the last one, which is count items, count -1. Okay, so and now I can take the last one and replace it with this one. Okay, that's pretty cool. So, and after that, I can quite safely just, you know, decrement this thing. Okay. So after that, current may have become invalid. So we have to wrap it around yet again, like so, by the amount of counts. It would be kind of cool to maybe create like an, how to say that? What is it called? A macro for this kind of thing. So maybe I could have created something like di swap, where I could specify the array and then the indices that I want to swap in here. So it's not really dead, it's active current and active count -1. Yeah, I think having something like di swap would be great in here, and just like, yeah, put all of that into this macro. So now look, so we mark the current thing as dead, we appending the current thing to the dead, we swapping current and the last one in the active, and then we decrementing the bubble. I think it's a good idea actually to have some sort of a macro for this kind of thing. So let's actually define it. So here is the body of the macro, and we're going to do di append. So here is the di stands for the dynamic array, and we're going to have I and j. So that's what we have in here. So in here, we are going to replace active with da, right? So since it's a macro, it's quite important to put it in parentheses. So the current is going to be basically I, and the count -1 is going to be, it didn't do the thing properly, so it has to be like this. And this thing has to be j. So furthermore, I think we're going to be passing array by the reference just in case. So I'm going to put this stuff like that. So, and even simplified it, right, actually greatly. Furthermore, so that's the problem. Like, we don't know the type of this thing. We really do not know the type of this thing, which is kind of annoying. So we can provide the type somewhere here. So let's put maybe, yeah, it's kind of annoying, but yeah. It is what it is. So let's also wrap it in do while to make it a proper statement. So this is a while 0, and maybe indent all of that stuff. And in here, I'm going to put this kind of thing in here. All right, so align like this. It's not di append, actually, it's a di swap. It's a di swap. So, and down there, where we use di swap, we have to use actually size t. I think that's a little bit easier to read, right? I think that's much better. And after that, we have to take the new thing that we got in here, right? So the new active current context, and take its RSP and restore that specific context. Let's restore that context. I wonder if like additional layer of indirection is going to make this entire thing a bit slower. Probably it will, but we'll see, okay, I really like where it's all going. So like making it a separate macro was a good idea, I think. I think it was a good idea. Let me double check it. I think for J, I would also like to wrap it in parentheses again, just in case, you never know. Just in case. What else do we have in here? So context, so it asserts, okay, but this is because it's contexts, so it's just a bureaucratic thing. Okay, anything else? Context underscore. I think that's about it. So contexts underscore. So something about control flow, but I think it's not in a, it's in a different place. Okay, this one is interesting. So like coroutine ID. I suppose actually it's not current, it's active items current. Yeah, so that's what it is. Okay, so and alive, how many alives do we have? It's actually just a live count. Yeah, there we go. So active, yeah. All right, and it completely failed. That's pretty cool. Out of bounds memory access. Very cool. Let's actually start with the simple counter. Let's start with the simple counter. And the simple counter didn't even run anything, surprisingly. Didn't even run anything. I wonder why. I wonder why. I wonder how. So when we initialize this entire thing, it is in fact active. Let's maybe do a little bit of a debugger as usual. When I build the counter, so I actually build with the debug information, so that means I should be able to do build counter and put it into JF2. Let's go. So break main. All right, let's run this entire thing, and this is what we get. So let's go into initialization. Let's step into that. So we got some contexts underscore, and we got some active, we got some dead. So all of them are empty. So if I just do that, so here's this thing. So we have one element count, blah, blah, blah. So in the active, we also gonna have another element, and that element is going to be 0. So initialization went perfectly, in my opinion. Okay, so now we're about to create a new coroutine. Let's step into that. So what do we have in here? So count, dead count is actually 0, so we're gonna skip this particular thing. That's pretty cool. Okay, now we're adding the context, new context in here. So now we should have 2 contexts in here. So that's pretty accurate, I think. And I think I already found what I forgot to do. I forgot to actually register that new ID in the active array. That's literally what I forgot to do. I think it's kind of important. So let's try to do that somewhere here. So coroutine go. So yeah, we just created this entire stuff, and now, and I really don't do any active in here. Yeah, that's actually true. Forgot about that. Completely forgot about that. Di append active. So now ID is active. Maybe we're gonna actually add that ID like in here, right? So that we first initialize the context and only then officially making it active by appending it into active. I think that makes sense. Okay. So what else do we have in here? So I think that's basically it. And okay, so it compiled. Let's try to run counter, and it works. And if I try to run echo, it seems to be working, right? So let me actually see. So if I try to do telnet, it will crash. It will crash at read, in fact. Okay, so we actually found the bug relatively quickly. Surprising, very, very surprising. Okay, it's probably because I ate some sugar right before the stream, so my brain is working really nicely now. So that's probably why. Okay, so maybe I want to actually commit that. Maybe I want to commit that, but I don't want to commit the these modifications yet that I did to the echo server, and also I don't want to make add these modifications, and I also don't want to add, I suppose, these modifications. and also this one. Anything related to coroutine, read, write, and so on and so forth. I think I don't want to do that. So let's actually, you know, selectively stage only the things that we want to commit in here. So we're staging that. Did I accidentally stage everything? Yeah, so I accidentally staged everything. So I want to unstage only this thing. So, and it is in fact unstaged. Okay, that's pretty cool. So C3, not staging that, that's for sure. Not staging that, not staging that. So I want to stage only this thing. And what we did in here is just like we're starting to reuse the stack, and we do not invalidate IDs, right? So this is the to-dos that we just fixed. Not that much code actually to fix that. And everything seems to be working fine, I think. Let me double check that. Let me double check. So we have a few examples of the counters. So here's the counter implemented in C. We also have a counter implemented in C++. And the difference here, by the way, is that this counter prints stuff from the lambda. Let me actually show you. So I really like this example. Right, so we create an extra coroutine in the C++ example that demonstrates how to use lambda. And the thing about lambdas in C++ is that if they don't capture anything, they act like function pointers. So this non-capturing lambda automatically compatible with the coroutines library written in C. Right, so if you don't capture anything, you can just pass some stuff in there. Maybe it would make sense to actually also put the ID, coroutine ID. I think it makes sense to do that. So let me see. So make b. There we go. Yeah. So it says 1 in here, right? So and then the rest of the things. We kind of have a similar thing for C3. Right, so we have a similar thing for C3. C3 also has its own lambdas. Here they are, and they're kind of similar. So they, by definition, don't capture anything. C3 just doesn't support closures. And because of that, lambdas are function pointers, right? So, and in here, I suppose I can also put the coroutine ID. This. So this library is written in C. And because of that, it is reusable in all of these languages. It's reusable in C++, it's reusable in C3. So I think people from our Discord server actually confirmed that this library is reusable in Python, I think, right? At least in Python 2. I think Spiritman tested it in Python 2. And in Python 3, it Stack Overflows, right? So right now, we're allocating the stack of 4 megabytes, if I'm not mistaken. Let me actually see. So where is the coroutine H? Yeah, it's not really H, it's C. Yeah, 4 megabytes, and that's not enough for Python 3. Anyways, but I suppose it's potentially reusable in all sorts of languages, right? So, but also if you have a managed language with like magical runtime, something may break in there if you use this kind of coroutine. So I wouldn't recommend to use this library for non-system languages, right? So I would recommend it to use for languages, for system languages with a minimal runtime, right? So because it messes with the runtime, right? So it creates its own stack, it has its own assembly, right? So you can't implement this library with a little bit of assembly, unfortunately, without a little bit of an assembly. Anyway, so I think all of the examples are working, all of the examples are working, and maybe I can even commit some of these things because they print IDs. So where's the to-dos? So here they are. And let's do commit. I didn't actually copy all of the to-dos that I needed. All right. Okay. So what we're gonna do? Fix. Actually, revamp. Is that how we spell this word? Is that a word in English? Revamp. I don't speak German. I suppose that's what it means. Revamp allocation, context allocator, right? So context allocator. So in here, we're gonna just do something like this. So that's the to-dos we fixed, right? And I'm gonna push that right into the return. And what I can do in here now, in fact, I think I can stash all of that stuff recompile it one more time, and run echo server without new modifications. Oh shit. Huh. I think I forgot to unstash the... Yeah. Oh shit, what the fuck is going on? I think I've... Yeah. What the hell is going on? I'm trying to... I'm trying to revert the buffer. Okay. Yeah. I forgot to unstash one curly brace. God fucking damn it. Anyway, I wonder if I can safely remove that additional curly brace and just commit it as a disk. Can I just do that without breaking my existing stuff? Right, so... typo. Okay, so I'm gonna push that. And I wonder if now if I unstash my thing, is it going to conflict with this entire stuff? Fuck you. How bad? Holy fuck! This is just one single curly brace, bro. Fuck off. I hate Git. I fucking hate, like, this is just a single curly brace, bro. And now I have to deal. Are you fucking shitting me? I didn't think it's that bad though, right? It's just annoying. Okay, so we're gonna compile now. Okay, that seems to be compiling. That seems to be compiling. So and now, if I stash this thing, and oh, did it? I didn't want to stash that thing. Which one can I? Okay, so I think I can do this one. So the only thing I want, right, so is just like run the new changes on the Echo server without modification that actually still works, right? So just to confirm that it's still working and still, yeah, that's everything I want. Okay, so thank you very much. Freaking software. Why software is so freaking annoying? I don't fucking know. Anyway, so we got this kind of thing. So let's continue developing. So now what we need to do, we need to implement this freaking coroutine reads and coroutine writes and so on and so forth. So so my fan is going off. I think it's just a side effect from the previous run of the server. So yeah, it is just a side effect. That's fine. It's fine, chat. Everything's fine. So essentially, we need to employ the technique where when the coroutine runs coroutine read, it goes to sleep. Right? It goes to sleep. And then the scheduler, once in a while, when you call yield, what the schedule is going to do is that it is going to call poll, right? It is going to call poll on all of these sleeping coroutines and their associated IDs, right? And that poll will give us information about like what, not really futures, but what coroutines should wake up. Right. So essentially how it works, you have an array of structures called pollFD, and within pollFD, you have the file descriptor that you want to poll on, and then mask of events that you care about, the mask of events. And then once you call poll, it may block or not block depending on maybe some events happened, and then it will return you the result through R events, saying what kind of events has happened there. And then you can make a decision of waking up those things or not waking up those things. So that's basically what we need to do, which means chat. We need to introduce another array in here. So you can have active futures, dead futures, and sleeping futures. That's very interesting. So, and we already implemented that mechanism in the futures library. Actually, I keep confusing the term futures and coroutines. In reality, they are completely different terms, right? So I should not be confusing them. Right, so we already implemented this kind of mechanism in future library for C3. So let me see what we have in here. I think it's C3 future, and here is the poll. So we need to find the runner that is responsible for this kind of thing. So where is it runner or is it, oh, I think I need to fetch all these things. Yeah, so let's actually quickly fetch because I've made some modifications to this library. So we have untracked file, so fuck all of that. C3 fut. So where it's all, yeah, there we go. So that's what we're doing in here. That's what we're doing in here. Yeah, so we do a poll, and then we go through all of them that we got, and we just waking them up. So this is the call that we have to perform in here. And on top of that, the yes, they're called bed. So the sleeping futures, like the hash map of sleeping futures is called bed, and the list of active futures is called kitchen because they're cooking. So we have futures that are sleeping and the ones that are cooking. Very funny, I know. What we need a hash map, and we don't have a hash map in C. So that's kind of the problem, chat. This is kind of the problem that we have in here, which is not really a problem. We do have hash map in C. So if we just employ nothing's STB library, it's not a perfect hash table as far as I know, STB_DS, but it's a hash table nonetheless. All right, so this is something that we can use in here. So I'm going to put that in the description. I'm going to put that in the description. All right, so I don't remember how to use it honestly, but we'll figure it out. We'll figure it out. Okay, good. So where is the coroutine? And I'm going to just like wget the whole thing in here, like this. Did we get it? Did we get it? I think we got it. So now what I'm gonna do, I'm gonna include stbds with h, and I also need to include all of the implementations of this beautiful, beautiful library. So define like this. So now if we try to build the whole thing, is it buildable? It seems to be buildable. That's pretty cool. So we have that. So the way it works, as far as now, you need to define a structure. You need to define a structure. So declare an empty type T. But I don't remember. I think there was a section of a non-function. Yeah, non-function interface. Declare an empty array. Yeah, so this is for dynamic arrays, but there should be also declare an empty hash map of type T, access the ith element of type T. Is that it? No, it's not really it. What was the structure? There was an explanation of how to use this thing, struct. Because yeah, this is what I wanted. Right. So your cell within a hash map has to be a structure with at least two fields, which is a key or a value. Right. And we need to create a mapping from the file descriptor to coroutine ID, right? Because the coroutine is sleeping on a particular file descriptor, waiting for a particular event to happen. So, and we need to be able to map that, because once we receive an event from the poll, it's going to contain a file descriptor. So by file descriptor, we'll have to find coroutine and we'll have to wake it up. So that's what has to happen. That's what has to happen. So yeah. So let's go here and let's create a new structure. The structure is going to be struct type sleep, and we're going to have a key, which is a file descriptor, and size t, which is a value, which is going to be the coroutine ID, right? So it's a file descriptor of the socket, and here is the coroutine ID. So that's what they are. And now we're going to create just something like this. It's going to be pointed to sleeping. Initially it's going to be null. So that's what we have in here. And there you go. This is the hash map. That's how we create a new hash map using this library, which is freaking cool in my opinion, which is in fact freaking cool. All right. So this is just like a sleeping feature. But we also need to know what it's sleeping on. That's what we need to know. What is it freaking sleeping on? So even in here, what we would even do? So we have a native socket poll, and where do we use it? Where do we use it? Aha, that's very fascinating. So we also need to have a dynamic array of poles, which are basically pole of Ds from this function. Right, for more information on how to use this particular API, I really recommend you to watch this previous stream on what do you need select pole ePole for, right? So we explored this API very extensively there. We implemented the thing that we're implementing right now, but for futures instead of coroutines, right? So they kind of is isomorphic, right? So both of them are kind of like asynchronous primitives. Because of that, like a lot of things, they share a lot of implementational things. It's kind of fascinating in my opinion, kind of fascinating. So isomorphism between coroutines and futures. Maybe at some point I'll write an article about that, some sort of a fancy article. The isomorphism between futures and coroutines. And it just can feel smart. It's just like, oh, maybe I will even have a PhD thesis about that. Who fucking knows? Sounds useless. It's academic bullshit. Academic bullshit. Anyways, I'm already doing slapping the code for 1 hour. I think the time has come for me to make a cup of tea. I haven't, yeah, so I need to make a cup of tea to continue. So we're gonna have this kind of thing. So we'll also need to introduce the dynamic array of poles. Right, so it's gonna be poles, but poles, not pools, but poles. Pole, yeah, it's gonna be pole of D. So that's what we're gonna have in here. So it's going to be the items, and in here we're gonna have the count and the capacity. So, and in here we also need to include the pole, right? Obviously this library is not cross-platform, which is, I mean, it's fine. We already made it not cross-platform by doing this kind of shit. So, and we explicitly say that the only supported platform right now is a Linux x86-64, right? So we're gonna add more supports in the future. Don't worry about that. So this is the only like platform that I care about, that because that's the platform on my laptop, right? So when I need to support more platforms, I'll just add the support later. Maybe we can even stream that. So, you know, adding support to ARM sounds kind of fun, right? I never programmed for ARM. I think it's a great opportunity to explore new platforms. Okay, so it's a sleeping, it's never used, it's defined but never used, and here we have to do something like static. Yeah, so here is the poles. So we can do poles and poles. This one is rather interesting. So how are we going to be doing all that? So we're going to be shoving this thing into the pole call, right? As you can see, here is the pointer to the items, and we're going to be shoving it into here, right? So that's where we're going to be shoving it. That's understandable. So after that, some of these things are going to be set as triggered. So that means, yeah, and we have their file descriptors that we can easily find within here in O(1), right? And then we'll also have to remove all of them. Yeah, this one's going to be interesting. So because we'll have to be removing them from the sleep and from the poles simultaneously. Sounds fun. Yeah. So looking up in a hash table sounds like a pretty heavy operation. But I mean, it's O(1) nonetheless. By the way, we also need to deallocate all of these things when we finish everything as well. I don't remember how we do that with stbds. So hm free. So free is the hash map and sets the pointer to null. Okay, so I have to do something like sleeping, and in here I have to free the poles items, right? So and also mem set the poles or poles. There we go. All right, so we're deallocating everything when we do coroutine finish. Yeah, so coroutine read. So we have to set ourselves to sleeping, that's for sure. And then we have to yield. And where are we going to be actually polling? I think yield is the one who has to do the polling. I'm pretty sure about that. So when you do coroutine yield, in fact, not within the yield itself, because it's a naked function with special assembly, but the function that it wraps, the switch the context function. I think this one has to do the poll, right? So what it is going to do is going to look who's sleeping right now, who is sleeping right now, how many of them. So we can do something like if you have like polls greater than 0, we have to do the poll call without any timeout. Yeah, so we have to make a decision. So if you have nobody active and everyone is sleeping, right? Nobody active and everyone is sleeping, we have to do the poll that blocks completely. That's one of the things we have to do. We have to do the poll that blocks completely. If you have some active and some of the sleeping, you have to do the poll with the 0 timeout that just checks for new events, and then continue execution as usual, right? So there will be a little bit of a work in here, I think. There will be a little bit of a work. So everything seems to be compiling here, right? So everything compiled. Okay. So the next modification that we have to do in here is this one. It's going to be pretty heavy logic, honestly. It's going to be pretty heavy logic. So because of that, switching the context might be pretty substantial thing in here. But again, so we're talking about the application that doesn't do too much computations, right? It just waits on I/O, right? And suppose switching context for this kind of stuff is fine, like this, like a heavy switch. But I don't know. We'll see. All right. So I need to make a small break. Yeah. So I need to make a cup of tea and the usual jazz. So all right. Let's continue. So what do we need to do in here when we get to this switch context? When we get to the switch context, well, I think let's not start with the switch context. I think we have to start with read. In here, when we get to the coroutine read, we have to put ourselves to sleep. That's what we need to do. And how are we going to be doing all of that? We have to essentially associate our current ID, coroutine ID, so basically current, it's not even current, right? So because the coroutine ID is this one, right? So we have to associate coroutine ID with that FD. So that's what we have to do, or the other way around. I think we have to associate FD with the coroutine ID because when we get an event from the poll, we need to find the coroutine ID by the file descriptor. So that's the basically association. If we take a look at the sleep, so here is the key, file descriptor, and the coroutine ID. So that's the thing we have to do. So that means we're going to be instantly adding this thing to the sleeping hash map. So stbds, and I think it's a hash map add or set. I don't really know. It has to be something like one of those. So there's a get I, insert, set. Okay, so let's actually keep going. Default put. Of course, who would have thought? Obviously, right? So this is basically sleeping, and we have to provide the key. The key is going to be FD, and the value is going to be coroutine ID. That's what we're going to have, and I don't think it matters what we're returning, right? So we're just like putting this thing in there. Does it say what it returns? It doesn't really say what it returns. Okay, so that's fine. So we just put this thing in here. On top of that, we have to append now this file descriptor to the polls. So where is the polls? Yeah, to the poll FD. How are we going to be doing all of that? This is very interesting. So di append by the pointer polls, and we're going to do struct poll FD. Maybe, you know what? I think I need to do struct poll FD like this. Let's call it PFD. I don't really know. So how does the poll function call that? It's called FDs. Yeah, but already I could have called FD, but it's already taken. Let's call it PFD. So within this thing, we need to specify these two events, right? So these two fields. We don't have to specify this field because it's a returned field, right? So it's going to be set by the poll call. All right, so that means we're gonna set the FD to this. And here we have to set the events that we expect. So we're expecting the read event, but as far as I know, it's not really obvious. You can't just say that there's no constant like a read event or whatever. It's something obscure. C3, right, so speaking of C3, one of the cool things C3 done right is that it was trying to give this kind of constant human readable names. Let me take a look at that. So if I take a look at C3 future, and what we do, you do sleeping, native poll socket. So yeah, poll subscribes, and if I take a look at the C3 futures echo server, when we were doing sleeping, yeah, so there was such things as subscribe read and also probably subscribe write, these kind of things. So if we take a look at how they are defined within the standard library, as far as I know, those things are not the POSIX names of this constants. They're, yeah, that's what they are. Polar D norm and pol WR norm. Why the fuck are they called like that in POSIX? I have no idea. So thank you, learner. Thank you. Like, I have a lot of criticism towards C3. I have a lot of things to say, but this is one of the things that you did right. So I really appreciate it. Thank you so much. Right, so this is a poll RD norm, and I can maybe verify this kind of thing in here. So I'm going to poll in, and there's like these are like aliases and shit. So it's so bizarre to me sometimes. Right. Anyway, so what we need to do in here. So where is the coroutine? What we have to do, so we're doing the read event, so that means we have to put this thing in here. Okay, so here's the PFD, and then we're just appending this entire thing in here. On top of that, what we have to do, since we put the coroutine to sleep, I think we have to remove that thing from actives, because it's not active anymore. It's sleeping. It's EP. So that's what we have to do. How are we going to be doing all that? So we need to do the usual swapperoonie, which actually brings a very interesting thought. Maybe I need to factor out the operation of removing an element from dynamic array, again, to yet another macro. I think that will make sense. So let's actually try to do that. Like, I'm going to try to write it one more time, and we'll see how we can factor out things. So I'm going to do DA swap, right? So I'm doing DA swap, and I'm swapping size T, so that's kind of important. In actives, right? So I'm swapping the current ID with the active last, right? So I'm swapping it around, and after that, I have to decrement this kind of thing, like so. So where is this second place where we use DA swap? It's basically the same. It's basically the same. We can even take a look at that. Yeah, so effectively, it's not even, so it's current. Ooh, this one is interesting because we have to not remove the ID, we have to remove the current. Right, because it's not what I think it is. Yeah. So that's correct. I think that's correct. So, and we literally have the same code. Look at that. We literally have the same code. You can literally clearly see these two lines in here. You clearly see these two lines. Okay. This one is rather interesting. So that also means we will have to switch our context to something else. So there will be a little bit of a yield, but we'll see. Okay. So let me do the following thing: append, DA swap. Let's introduce DA remove. So to remove something, we will have to provide the type. Unfortunately, DA swap wants a type. We'll have to provide DA and I, right? That's the operations we have. And in here, that's what we need to now implement. So this is going to be DA. This is the current. this is DA, and it's going to be passed by a pointer. So passed by a pointer. I'm not sure if I have to do the type in here, but whatever. So DA like this, and I think that's basically maybe I have to call it DA remove unordered. Yeah, because it doesn't preserve the order, because it shuffles things around. So to be explicit on that, I think it makes sense to actually put that in the name of the macro. All right, so let's put this stuff in here. So this is going to be backslash, then in here, and this is while 0. Cool. So we've got this kind of thing. So now I can do something interesting here. Remove unordered, size t, active, and what I'm removing the current thing. So that's what I did in here. That's pretty cool. That simplifies a lot of things, hopefully. I think it does. Right, so we append this file descriptor to that and that. So DA swap I set. So in here, what I can do, DA remove unordered, size t, active, current. I can remove that. So this is finished. When I finish the routine, I mark it as dead, then I append. Oof, I have to be careful here. I'm not appending the current, actually. I have to be appending. Ooh, I just found a bug. This is dangerous, by the way. Right, so I'm appending the ID to that. Yeah, ID to that. Then I'm removing that thing from the active. So additional layer of indirection actually screws up a little bit with my brain. Right, so and then I restore the context with the next one. Yeah. Have to be super careful how we use all these things. So I feel like at some point I'll have to go through all of the places where we use current. And by the way, here, again, another bug. So this is not the current ID. It has to be active items like this, because it can be shuffled around and stuff like that. So we have to be super careful. So where is another current? So this one is dead, and then we're removing it from that one, and there you go. Okay, the current ID, and then something with my monitor. Okay, so I think that's it. Now I'm super paranoid. God damn it. I'm super paranoid now. I think that's it. I think I didn't see any more bugs in here. Anyways, so that's the current ID. Then I just put it in here, then I put it in polls, then I remove it. And now I have to switch to the next context, essentially, right? So I need to switch to the next context. How I'm going to be doing all that? That's a very good question. Essentially, what I have to do a yield. So, but I'm already doing kind of a yield, don't I? Already kind of doing a yield. This one is dangerous, actually. I need to think, because yeah, the next logical thing would be to just like update the current, right? So just do current +1, or you know, the usual thing, current +1, and then just mod it with active count. But you may end up with the count like after you. What if all of the coroutines are sleeping now? What if all of them are sleepy EP? This one is dangerous, right? So if the active equal to 0, you have to basically do the poll, right? You have to basically do the poll. But I was expecting to do the poll in coroutine yield. In coroutine yield, this is where I wanted to do the poll after I capture the current context and put it to sleep and stuff like that. So this one is bizarre, to say the least. This one is bizarre, to say the least. What we can do, I think we need a yield, like a very much similar yield, but the one that accepts parameters. I think that's what we need to have in here. The one that accepts parameters. So something like void coroutine sleep for sleep on read, and we're gonna accept only FD sleep on read, and that one is going to be actually, believe it or not, similar to yield. It's going to try to save all of the environment. So as you can see, it's also saving like RDI or whatnot. Doesn't really have to, but I mean, it doesn't matter. So we're saving RDI. Then we're gonna be passing RDI forward. So yeah, here is the we're moving current thing to RDI. And then we're switching the contexts. This one is complicated because it needs a more sophisticated yield. It needs a more sophisticated yield, maybe a yield that accepts sort of like optional parameters. Not quite sure. Sort of like optional parameters. So I need to know exactly the call convention in C Linux, right? So Linux x86-64 call convention registers, right? RDI, RSI, RDX, RCX, R8, and so on and so forth. So something like that. So let's actually put them in here. So this is specifically integer arguments, right? So for the floating point arguments, it's kind of different, right? So here is the Linux x86-64 call convention. So coroutine yield is doing something interesting. It is doing this, it's saving the context, right? So on a stack, and then passing the current stack pointer through RDI. That's what it's doing. I want to have very much similar functions that do the same, but then pass additional parameters to the switch context. So the thing they're going to be also passing, they're going to be passing information whether we're sleeping, right? So this is a sleep. And I think for the sleep, we may even have some sort of enumeration, like a sleep mode. And basically, we can say SM none. So by default, 0 is going to mean we do not sleep, right? So, and restore context, I suppose. So this is actually switch context, right? So it's a wrong one. It's actually a wrong one. So switch context by default is going to have a sleep mode equal to 0, and that means it will act like a regular yield. Then we can have sleep mode read, so we're waiting on read and then on write. So that's the additional parameters in here. I think switch context has to be a little bit closer to the yield because they are kind of related. They are in fact kind of related. So when you just call the yield, we, for the second argument in here, so where is the call convention? So RDI is the first argument, RSI is the second argument, right? So that means RSI, we're gonna just put 0 in here, 0 into RSI, and I think you have to put $ in here for the constants, which means that when you called yield, the sleep mode that we're doing is going to be none, right? And we're just gonna be doing a regular yield. So switch, and that's all we can do in here. So switch upon SM, and if it is SM none, we're doing the usual thing, right? Okay, so, and then we can now introduce more interesting things, actually copy paste the whole thing in here, and we can say coroutine yield sleep read. And we can pass a file descriptor in here. And the file descriptor, just like, you know, let's ignore that. The file descriptor is going to be in RDI, right? It is going to be in RDI. We're saving it nonetheless, but it doesn't matter. None of that matters. So that means in RSI, we must put 1 to indicate that we're now in SM read, right? And then for the third argument in here, which is going to be in RDX, we'll have to put the RSI, right? So whatever we have in RDI actually. I'm modifying the wrong thing. Just a second. Yeah, I'm modifying the wrong thing. So it has to be RDX, and we need to move RDI into that. But RDI is already modified in here. So that means we have to put it somewhere here. So first we move in, RDI into RDX. Then we move in the current stack into that and into the RSI there. So we can even specify what kind of parameters we have in here. So this is RSP parameter, this is SM parameter, and in here we're going to have the file descriptor parameter. Right, so this is the file descriptor. So for the yield, the file descriptor is going to be basically 0, right? So this is going to be RSP, and this is going to be SM. Yeah. So that's what we have in here. And we're going to have a similar thing for the read. Very much similar thing for the read. For the write, I'm sorry. So this is going to be write. So it's D, but instead of 1 in SM, we're going to have 2. All right. So that's how we're going to be approaching this entire stuff. That's how we're going to be approaching. So we're saving and simultaneously telling what kind of operation we want to do in here. So we're gonna have SM read, SM write. Okay, let's so let's actually say that this one is not implemented yet. To do SM read. So I'll probably have to implement to do super quick, or maybe I'm gonna stall it from knob. So this one is gonna be write. I'll probably have to steal it from knob, so this one has to be unreachable. This one probably has to be unreachable. So there's a lot of things that are not fully reusable in here, but maybe we can factor out this kind of stuff into a macro. Who said we can't do that? I think we can do that. So it's basically different kinds of yields that are parameterizable. So that's what we're doing here. That's pretty cool. That's pretty cool. So in here, yeah, this gives us an opportunity to actually do polls and sleeps in a single place, which is good, right? Which is really, really good. So maybe this, like a sleep mode, has to be called something different. Maybe it's something like a yield operation or switch operation or something like that. But I already kind of assigned a name for this field, but I may change it in the future because I feel like it's not really sleep mode. It's more like an action, like a yield action. Now we have different flavors of yield action. And this is what I wanted actually originally, like different flavors of yield, but they're all handled within a single place so they can reuse some of the same code, right? So it's not spread around in different places or anything like that. So I think that's good. So, and the code that is responsible for all of that stuff, right? So you see switching the context and stuff like that has to be in SM read, because this is where we do the switch, right? Look at that. This is where we do that current +1. We do it in here. And that's why I felt like I'm doing this thing in the wrong place, right? Because it has to be somewhere here, right? But how do I move it in there? Well, I have to do this a little bit additional assembly that forwards additional parameters to this switch context. Otherwise, I won't be able to do that. So that means here, what I have to do is I coroutine sleep read, and I'm sleeping on FD, right? So I'm just like sleeping on FD, and correspondingly, I have to do sleep write. And what's funny is that after this particular yield, so it effectively performs a single yield, and it's not going to return to this coroutine until the read or write operation is available on that specific file descriptor. That's what's going to happen. And as soon as we get back to here, that means the read or write operation is available on that file descriptor, so we can actually perform it, try to perform it. Right, so what we're going to do in here is just like fd buffer n, and we can effectively just return this entire thing. Actually, that's it. All right, so if we move all of the heavy lifting into these things, what is left in here is just like calling all of these things and forgetting about them. and then you are the one who's going to be handling all of these like errors and so on. Okay, that's actually very smart. I really freaking like that. I actually really freaking like that. Huh. That's pretty cool. All right, so can I just try to compile the whole thing, because I'm pretty sure it's not going to compile right away. So what do we have in here? SM none. This is an enumeration. Yeah. Okay, let's go to the compilation errors. Restore context, it doesn't like that the restore context is... that's why restore context is actually down there. Well, it's not defined within the, what is it called, header, right? So that means I have to kind of follow the order and stuff like that. Coroutine ID, it doesn't like that coroutine ID is not... Really? Coroutine H? Don't I have coroutine ID here, bro? I do. Don't I include... I don't even include my own header. What the frick? Okay. Coroutine H. How did that happen? I don't fucking know. So to do, we don't have to do. I think I want to implement the to do macro. I think it's a useful macro from Nob. And honestly, I kind of want to move all of these macros into Nob at some point. But I mean, this freaking type, it's kind of annoying me. So the thing about the iappend is that it never really needs to specify the types, because it just gets the size of the element from here. But I mean, we can always just like allocate some scheisse like char, you know, t, and we can say that its size is the size of the freaking element like that. Right, and then instead of assignments, we can do mem sets. Oh my god. Okay. But I mean, the compilers are smart nowadays, so mem sets are probably going to be fast, so who cares? So, yeah, okay, I'm not going to do that right now, but like something to think about. Something to think about. Okay, so to do, can I just steal that from nob.h? All right, so nob.h to do. Yeah, it's a very simple one. It does the abort thing, and it's very convenient. Like this. Okay, what else do we have in here? Unreachable is kind of similar from the same family of things. I'm not going to be using Nob for this library because it's a very lightweight library. I think adding dependency on Nob is a little bit too much, especially if we just depend on the macros from Nob, right? So it's a very simple macros. I can just copy paste the macros. Okay, it doesn't like that I didn't include something for read. I think what I have to do here is include unistd. unistd.h, okay, and everything seems to be compiled. That's pretty freaking cool, mate. That's pretty freaking cool. That's pretty freaking cool. That's pretty freaking cool. Excuse me. So I kind of want to test the coroutine sleep read and sleep write, that it actually passes all of these things correctly. So one of the way we can test that, honestly. You know what? You know what? You know what? You know what? We can expose coroutine sleep write and read into the header, into the API, right? And then, because look, this is not really needed to be like this. You're calling original libc function anyway. So what we can do in here is just like expose that, and it's up to the user to call this libc thing. I think that's fair. Yes, I think like it's so thin, it doesn't need to exist at all. Let's just expose these things. Let's simply expose them. I'm gonna do coroutine.h. So instead of that stuff, we're gonna just have this thing. Attribute is not needed in here. And let's just have read as well, so write. So because of that, we can just remove this thing. So it's up to you to like sleep on that until it's ready, and then you return back. All right, so now it is exposed. It is in fact exposed. So, and C3 is complaining a little bit. That is understandable. That's totally fine. So we have to do in here instead, we have to do sleep read and just do it like that. So let me do coroutine.h sleep read, sleep read, sleep write. And we're also gonna only accept file descriptors. File descriptors. Sleep write. So what we're gonna be doing in here, so write TCP socket. Maybe, yeah, it makes sense to probably get rid of this entire stuff completely as well. Yeah, I think so. Let's actually do it like this. I'm gonna get rid of that and try to recompile it one more time. So yeah, the API is evolving, right? So we just let the low level stuff to drive the API design. That's pretty cool. Echo, example, echo 19. So what we're gonna be doing here, we're gonna be doing coroutine sleep read, and we just take the client sock and sock. That's what we do. So this is our yield. And after that, we can just call the regular read in here, and we can unwrap it and be sure that it's not going to block. That is very freaking cool. That is very freaking cool. I really like that. So just sleep on the read and then call this entire stuff yourself. Fair. Totally fair. Okay. So it's still gonna complain about 26, right? And it's a similar situation. We just do sleep write, make sure the write operation is available in there, and then just do the write. Just do the write like this. And it's compilable. Okay, so it's not going to work, obviously, right? So, but it's compilable nonetheless. We can try to run, obviously, the echo, and I think it's going to fail on trying to read and write. So it's going to work at first, but then as we try to sleep on the read or sleep or write, it should hit the to-do. It should actually hit our to-do, and I think we need to test that. Coroutine.c, coroutine.c. So it should actually hit this thing. So let me actually put this to-do in here. So because I'm not sure about this code. I'm actually really not sure about this code. So yes. So let me rebuild everything. Let's try to run the regular counter. The regular counter just works. So what about the echo server? This is wrong way to run it. Let's do it. Build echo. It is listening. Okay. So if we did everything correctly, if I try to connect to telnet, it's going to hit the to-do. It did in fact hit the to-do, dap. So that's actually pretty perfect. So, and one of the things I can do in here, by the way, I can now print all these values and make sure that they are what I think they are. So RSP is going to be something. SM has to be 1. Well, I mean, we know that it is 1 because we hit SM read. And FD has to be, I think, like, so 0 is std in, 1 is std out, 2 is std error. So it has to be 3. Right, if we did everything correctly, I think FD has to be equal to 3. We can kind of confirm that. So, you know, just a simple sanity check. Simple sanity check. So this is going to be echo. And then telnet, boom. It's actually 4. I mean, understandable. The server socket is 3 and the client is 4. Yeah, so that is correct. That is correct. So again, we can double check. Std in is going to be 0, out 1, error 2, server socket is 3, and the first client is going to be 4. So I think the sanity check has been passed in here. So we're passing parameters correctly. We do in fact passing parameters correctly. So because this is very dangerous, right? So we're passing parameters like this using the call convention and stuff like that. By the way, this arch tag is all of the places where you need to make modifications if you're gonna add a new architecture. So it's kind of important to keep track of them. So yeah, so ARM support requires modifications in all the arch places. But suppose we can compress some of this stuff, right? So we can move saving all of these registers into special macro, right? So I think all of that stuff is kind of compressible. I think so. So anyway, what we're gonna be doing in here? What we gonna be doing in here? Gonna be doing in here. Gonna be doing in here. Gonna be doing in here. So This is also kind of the current ID, isn't it? Yeah, it is. So might as well, instead of like, you know, calling this function, I think calling coroutine ID here is kind of too much because it's an external function. It is an external function. So the funny part in here is that you may end up with 0 in here. Right, you may straight up end up with 0. And that's kind of dangerous. And by the way, since you're yielding, in the current ID, you have to save the current RSP. I feel like, chat, this line has to be also here, right? So before we do the read, we have to save the current RSP. And because it's going to be present in the read and probably going to be present in write, we have to put it in here. It's a common line in all of these things. It is in fact common line in all of these things. And what's funny is that as we switched to the next operation in here, we're going to be restoring the context, and we're probably going to be restoring the context in here as well, and probably in write, which means that this line has to go after all of these things, like this. Okay, so we're getting somewhere. We're actually getting somewhere, and look at that. So we can end up with active count equal to 0 in any of these things. So which means that yeah, we actually don't have to do current plus 1 because current is now updated. We can just keep the current the same. But one of the things we have to do, I feel like, we have to mod the current like so. Right. So just in case, if it was already the last thing, we need to wrap it around. And then at some point, we may get the situation that we don't have any single one active. No one's active. So we can get this kind of situation. And I feel like we have to handle that situation for all of these branches in here. I feel like that's what needs to be done. So because of that, I'm gonna move this thing in here, right? So which means that we don't have to mod it in here. We can just make it like that, and then in here we can just do plus 1, right? So no sleeping mode is just incrementing current to the next one. Read sleeping mode is just putting this entire thing to sleep without any increment because the current now points at a different context anyway, so whatever. And then wrapping around just in case. But before trying to wrap around, we have to first check if there is anything to wrap around. Right, because again, if this thing is equal to 0, you're going to be dividing by 0, so that's straight up no. Okay, that is very cool. So this is such a simple operation, might as well just do something like that. Look at that. Isn't that readable? I think that's pretty freaking readable. Bruvskis. Bruvskis. Okay, so, and we can even start repeating this kind of operations in here, right? So because it's just read, the only difference between read and write is going to be this constant. So RD, WR. Is it WR norm? I think it is WR norm. I think, yeah, there we go. So that's what it is. So this one is unreachable, which is totally fine. Then we do this kind of thing. And in fact, if we're going to end up with 0 active in here, this is probably where we need to do the poll. I think so. I think that's basically where we need to do the poll. Yeah. So to do like here is the poll, right? And so this is where we're gonna just straight up block. We're just blocking until one of the sleeping futures are gonna have something. And in fact, we need to assert that we have at least somebody to sleep on. Right, so the amount of poles, current poles, has to be greater than 0. Otherwise, like, it's kind of a weird situation where you have 0 active and 0 sleeping as well. It's just like, what kind of situation is that? So that's a very dangerous situation, meine Freunde. And by the way, I still have underscore in the context. I will probably have to remove it at some point, but I mean, it's whatever. Okay. So yeah, that's pretty close to what I want in here. Saving this stuff, then making a decision, either putting one of them to sleep or whatnot. And what I'm thinking in here, we need to probably perform the polls. Right before trying to switch this entire stuff. I feel like that's what we need to do. It's getting into interesting places. Let me try to compile this entire stuff. First try. Compiles first try. Compiles first try. Maybe we can take a look at how we do that in the futures library. How do we do that in the futures library when we receive some stuff? All right, so we're just handling some stuff, and if anything, we just put all of the necessary features to sleep. Okay. So after that, so this doesn't matter. We perform the call, right? And whether we have any timeout or not depends on whether we have any active or not. This one is interesting. So I think I can actually copy paste this code into here, like straight up here. I think that's kind of interesting because that means we can make a timeout. Okay, so active kitchen is actually the active things, right? So active count, and if it's 0, that means the timeout is going to be -1. So in a timeout -1, let me see what it means, timeout. So specifies the number of milliseconds should be waiting. Note that the timeout interval will be rounded. So specify a negative value in the time means infinite timeout. Okay, so if you don't have anybody active, right? If we don't have anybody active, we're using infinite timeout. If we have some people active, the only reason why we're calling poll is to check if there's something there. Okay, so that makes sense. So after that, we perform the actual poll in here, right? So we have to do polls, which is going to be items. And in here, we have to do polls, which is going to be count. Right, and it's going to be timeout. I wonder if I can just like inline it, but let's not inline it. So when if we get a negative result, that is bizarre. So when poll can fail, so points outside, it's a memory issue. Signal occurrence while, so it can be basically interrupted by a signal. You know, for now, I'm going to just say, you know, fuck that, std error. You know, let's call it unreachable. Right, so poll. So this is basically unreachable, at least for now. Or maybe to do. So maybe we should, you know, handle it at some point. Okay, so after that, after we did the poll, what we have to do, and this is very interesting, we have to go through all of these things, all of the polls, and check there are events. And if there are events are present, we have to wake up all of these coroutines, like we wake up features. All right, so that's pretty cool. I'm gonna do size t and iterate through all of the polls in here, like so. Here are the polls. And yeah, if we need to wake up, we also need to remove them from the polls. So this one is rather dangerous. All right, so that means maybe I have to iterate this entire thing from the beginning, from the right. So then I can easily remove things as I go, or not. I'm not really sure actually. Well, probably not. Yeah, probably not. Anyways. So if polls items I are events, so we got some are events. What we have to do, we have to now take the file descriptor that we have in here, right? What the fuck is going on? So we take the key, fd, and we have to look it up in a sleeping hash map. So this is very important. We have to look it up in a sleeping hash map. It would be kind of cool if you could actually add additional stuff into the poll fd, but I think it's too much to ask from a POSIX API. Right, so stbds hm-get. So yeah, so we can just take this value. All right, so hm-get. So we're getting this fd and we're getting the new ID, right? So this is the new ID that we have to effectively put into active, right? So we have to put them into active. So after that, I have to remove this entire thing. Right, so here's the ID. What I need to do, I need to do di remove unordered. So this is going to be polls. And so we have to also provide probably struct, what was that? Struct poll fd, poll fd. So I'm doing that. And I'm removing I. So I just removed this thing. Then I need to remove it from the hash map. So hm remove del. Yeah, hm del. So I'm removing this thing. Hm del. Oh, this one, by the way, has to be sleeping. Hm del sleeping fd. Okay. So we're removing the current poll, we're removing the current fd from this kind of thing, and we need to do di append to the thing, di append to the active. So now this ID becomes active. So that's what's going on. This ID becomes active. And what's funny is that as we remove this I, if we remove this I, we should not do ++, which means we'll probably have to do something like this. Otherwise, ++I, which is kind of similar to what we had in, yeah, this is it's kind of similar to that. Believe it or not, it's very much similar. All right, so that's pretty cool. So we put something to sleep or switch to the next thing. Then we did a quick poll, depending on whether we have active or not, right? So just a quick poll. So looking through all of these polls, right? So we're getting the FD from the sleeping. So this is the coroutine ID. So we remove the current poll, then we remove that FD from the sleeping, and we making this ID active. So that's basically what we're doing. That's essentially what we're doing. All right, that's pretty cool. And after that, we kind of have to do active count. And this one is really interesting. So I suppose if everything is done here correctly, this thing should never become 0. Because if it is 0, and this is what we check in here, by the way, if it is 0, we go to the full timeout, like infinite timeout. If it is 0, we go into the infinite timeout. So as soon as something happens, it will be put back into active. So this thing will never, if everything correctly in here, will never become 0. So that means this particular part is not needed anymore. And the only thing that is really required in here is just to assert that this thing is, you know, not equal to 0 or greater than 0, or something like that. How often do we use asserts? We use asserts in quite a few places, but I mean, yeah. So asserts don't really play well with our stacks. There's something weird about them, but I mean, nonetheless. I think that's it, by the way. I don't think there's any to-dos left. Yeah, so there's only one to do for the poll. There's only one to do for the poll. But apart from that, I think that's basically what I want to do. Basically. Yeah. So... And it's kind of similar to what we're doing in the C3 futures, kind of similar. Oh boy. All right. So we also do the polls. But to be fair, maybe we should also have additional check in here that if you have any sort of like account or whatever, so if you have 0 polls count, don't sleep, don't even try to call any of that stuff. I think that's fair. Right, so if you don't have anything in the polls, like what's the point of even doing any of that stuff? There's no point to do that stuff. If you don't have anything in the polls, you at least have something active. You have at least the coroutine with the ID 0 active. So, yeah. So let me try to compile this entire thing. I don't know if it's going to work or not. Okay, copy paste, by the way. So, so it says something about STB. So what you don't like, my friend? Right-hand operator of comma expression. What the fuck are you even talking about? Brovskis. Is that a known thing? So right-hand operator has no effect. Ooh, let me see. I'm gonna go to nothing's repo because I feel like I vaguely remember this thing. Issues for it. Yeah, there we go. So when using HMDL to delete a key from a hash, I encounter warning. Because HMDL is a macro that returns a successful value, it's roughly the macro equivalent of function return value is ignored. Warning is trying to cast to. Okay, so that makes sense actually. Thank you so much. Yeah. Wait, did it run the thing? I don't think it ran the thing. So my fan is going off, probably because I opened GitHub. All right. You know, the freaking classic. Okay, so it doesn't complain anymore. Let me double check my HTOP super quick, just a second. So something is going off. It's just OBS. I guess it was Firefox, right? So it just increased the temperature. The fans went off. Right, so they should calm down soon, hopefully. All right, I'm a little bit scared. Like I didn't know if it's going to work or not, right? So everything compiles, right? So, but we're talking about like a very low level languages, so you never fucking know. And this is a rather complicated logic, honestly, just for the switch. But again, if you never use like polls, this is going to be super fast because you skip all of that stuff, right? You don't really have to care. You don't really have to care. Okay, so using an entire hash table and shit for the coroutine runtime. I'm not sure if using hash table here is a overkill, or like at least not really using hash table, but bringing STBDS is an overkill. Maybe we could implement our own hash table, because what we need to do, we just need to map one number into another one. Maybe we can just have our own hash thingy, right? So because I feel like STBDS is too much of a dependency in here. It's just like it's it's 2,000 lines of code. So by itself, it's a rather small thingy. Majority of the code is comments anyway. So maybe it doesn't matter. Okay, so let's do recompilation one more time. I'm gonna just run the counter just to do the sanity check. So does the count? Okay, the counters work. Oh, and now the ID. I think the IDs are stable now. I never noticed that because it's the second coroutine that was longer than the first one. I think that was the case. I think that was literally the case. So if I take a look at the example coroutine C, yeah, it's the second one. If I now swap them around like this, hey, Emacs, stop. Don't be silly. Yeah, so now it's the first one that is longer. Everything seems to be okie dokie, karaoke. Okay, so you know what I'm thinking? In the Echo server, I think another thing I can do, I can also do a similar thing for accept. I don't remember when accept becomes unblocked. I think it's either read or write. And let me take a look at the Echo server from the futures. So accept. Okay, what are we waiting? Sleeping on read. Okay, so here we're sleeping on read, so that means we have to put a read in there. So here's our echo server, so that means I can do something like so sleep read. I want to quickly copy paste this thing in here. So now this is the server socket, sock. We do sleep read, and now I can do accept, and I don't even have to do this kind of shit anymore. Damn. Bro, if this is going to work out, this is going to be so freaking awesome. Look at this code. It is so concise. It's insane. Yeah, you just sleep on the read, and then you can just safely accept. We can even move this thing down as a, what is it called, as a lambda. So it's like a single function now. We can even inline that stuff, and it's going to be fucking awesome. And it's going to look like a threading, but it's not really threading. It's coroutines and shit. Bro, I'm so excited actually, and I'm also scared because I'm pretty sure it's gonna segfault right away. Right, so okay, let's do. Okay, let's just jump into it. Let's fucking go. Fuck. Okay, so out of memory access, understandable. So it went into switch. It tried to switch the context. That's understandable. Ooh, and it actually went into like stbh put key, some shit like that. Yeah. So it actually went into pretty nasty places. I wonder if this is because we ran out of memory. Maybe the, you know, maybe it wants a bigger stack, right? So let me take a look at what the size of the stack we have in here. So coroutine.h, not really .h, but c. So now we have 8 megabytes. What about 4 megabytes? Let's about 8. Let's increase the stack one more time. Right, so is it going to be fine? Nah, it didn't help. So I kind of, yeah. So it did sig action. Was it really out of bounds or was it just segfault? That's a good question, actually. That's a good question. So yeah, can I try to open this thing in GF2? Okay, let's just run this entire thing. Okay, so coroutine switch. We tried to do sleep. And what exactly happened in there? Force debugging. Is that because the RSP went to a weird place? Maybe it just like overflew. Jumput. Am I using this correctly? Is that because sleeping is null right now, which is fine, because that's how you do it. That's how you actually do it. But maybe I'm just using it incorrectly. Wait a second. hm put non function int. Yeah, you just do it like that, so that's understandable. And in all honesty, maybe I should just like try to switch. Okay, let me try to do it one more time. I'm glad that it's reproducible both like in runtime and in a debugger, so I can at least debug this kind of thing. So coroutine switch context, right? So let's just run this entire thing, and it is running in here. So we can take a look at the values that we have in here. So it's RSP. What about SM? SM read. So I suppose it is coming from the accept thing, right? It is coming from the accept, which is understandable. So SM read, NFD is 3. That is perfectly understandable. That is perfectly understandable. Okay, so we're saving the current thing. That is cool. So we go into the read. So this is the current ID. So it's actually 0. So that means it's main ID in here. Okay. hput sig, and it already failed with this thing. So with hput. Coroutine switch. So, but who failed? Who failed? So, and it failed in a really funny place. So you have, if you take a look at A, is that because A is 0? Because, yeah. So maybe I should use an array instead of hash map. I can try. I can try to use an array instead of hash map because I don't think maybe I'm using this hash map incorrectly. I feel like I'm using it incorrectly, but I'm not 100% sure. Because it's a bizarre error. It's a bizarre error. I'm also a little bit tired, so okay. What about maybe 10 megabytes? Yeah, it's the same thing. The same thing. Arrow F. I wonder if maybe there is some warning, like maybe I'm just like using it incorrectly. So let's try to Google this thing up. Some issues. Free incorrect documentation of the text, direct memory leak. Okay, possible leak when using SH default. I'm going to text memory leak. Segmentation fault. Sleeping. I'm sure I'm missing something. I'm sure I'm missing something. It's a file script hm put. String hm put. Key value. Key value. Can already printing hash map. It's just doing that. So just the put, and then here h. We didn't even get to that point. We didn't even get. So something is really nasty. Something is really nasty. What if we don't do that, right? So we just like not add that there, right? I mean, it's kind of dangerous. I understand that, but I mean, like, I just want to test what's going to happen. Oh, yeah, it's working, but it doesn't put this thing into the hash map. Maybe the hash map is not working correctly with our thing. I don't freaking know. We can, okay. So let's use dynamic array instead of this thing. Seriously. So sleeps, and we're gonna just do sleep items, and this one is going to be size t, count, and the capacity. Right. So I think that's annoying. Like, you need a hash map for efficient lookup and stuff like that. Otherwise, it's not gonna work well. But I don't know. I don't really know. So static sleeps. So let's go through the compilation errors in here. Yeah. So what do we have in here? So this is hput, and what we're doing here, we're gonna do dappend. Dappend sleeps. All right. Sleep fd id. Actually, it's a key, and value is id. And we probably, yeah, so that's about it. I'm going to comment this thing out, hm3. So, yeah, this is basically the same thing. Basically the same thing. Also, this one is reused in so many places. Maybe I should just... I don't know. So, okay. So I'm sure I'm just missing something very freaking stupid, as usual. Something very... And I don't like... So, and then deleting is going to be annoying. Honestly. Deleting this entire thing is going to be super annoying. Oh boy. Though... Actually... Wait a freaking second. Do we need... So what if we have a parallel array? So you have polls, right? So poll. All right. So this is a poll. And then you have ID for this thing. And they are parallel and they are corresponding to each other. They do in fact correspond to each other. So now through the poll, you found that this one was triggered. You can use the index of the poll to get the ID of the coroutine to recover, and then you just delete them somewhat. Okay, so, and because of that, sleeps can be indices. So indices, so asleep. So we have active dead and asleep. And they are, so if you do DI append unordered on asleep and pulse simultaneously, they're gonna stay in the same order anyway. Bro, you don't need, like that solves it. That fucking solves it. You don't even need this Scheisse Brovskis. You don't even fucking need that Scheisse Brovskis. So let's actually even remove that so completely just in case. Yo. That simplifies so much dramatically. Okay, so when I do an update, asleep, what I'm saying is just like put ID in here and remove all of that shit. We don't need that. So asleep. And we're just appending them basically simultaneously, don't we? Yeah, we do. So that works out. What else? What else do we have in here? HM get. All right, so to get the ID, what we have to do, we have to now do asleep. I'm pronouncing asleep in a really weird manner, I know. Okay, so this is that. And now, here's the fun part. I can do that, size T, asleep. Since I'm doing that simultaneously and they're parallel, they're gonna stay in the same order. That's genius, actually. What the fuck? Why didn't I think about that? That's cool. Bro. Alright, so let's fucking go. Which I'm free. We don't even have to do that stuff, but we can do asleep. Like this. And then we can memset that thing. Memset that to 0. Size of asleep. Can I align? Look at that beauty. Holy scheisse. So there's a little bit of a, how many? There's a 5 of these things on context, active, dead, poles. Okay, so they're kind of like, you know, they have corresponding things. So that's the entire to the state. No hash maps, by the way. No hash maps. Asleep. So it's just like, see, I don't need you chat to have fun. I can have fun alone. Right. So let's see. So is the H-top spinning? H-top is not spinning, I think. I didn't see H-top spinning. Look at that. There's no spinny. Yeah, that's oh, there's OBS, but I mean OBS is an ass. So telnet, let's fuck. Oh my fucking goodness! Look at that! Look at that! And it fucking responds. So now I can do telnet and fuck you, Leatherman. Fuck you. So what the why? Okay. Okay, that's super fun. But I mean, it kind of tried. It you know, it tried, I think. All right, so what the fuck is going on? Let's find out. But we almost there, right? So it didn't crash immediately. So let me see what the fuck is going on. It accepted the connection. It couldn't accept the second connection, though. Unfortunately, I have no idea why. Sleep read. We're just doing that. Sleep write. So everything is marked as. Yeah. So this one is marked as non-blocking. That is cool. Then we sleep for read, and this gives us an accept and stuff like that. Then we set a non-blocking for the client, and then we create a new coroutine with that. So then we do on another sleep read, which will basically trigger yield and then trigger this thing anyway, right? So that's going to be a correct thing here. All right, so we're allocating some memory. That's fine. It's just a little bit of dynamic memory. And So we do sleep read on this particular socket. Didn't see anything special per se, honestly. See anything special? How do I even debug that? How do I even debug that? That's a good question. I'm looking at a really weird version of coroutine. So sleep right. So if we do sleep right, we save everything. So RDX, we're moving the current parameter into RDX, and RSP into RDI. So this is the first parameter, and then 2 into RSI. That's how we know. Okay, so that's the current active. I'm not sure if ID is such a great idea, honestly. Yeah, we append this thing to a sleep, and then append polls with the FD. Yeah. And then we remove the current thing from the unordered, but we don't increment that thing. So after that, if it's right, we do ID, then we do that, and then we remove current from active. So, but we remove index, right? So this is the index that we're removing here. So that's understandable. Okay, so if we have some polls in here, so if we have 0 active, we just choose the timeout. Okay, so if we have triggered something, so that's the ID, right? So that's the ID that we need in here. We remove unordered from the polls and from a sleep, and then put in active back. So then we wrap this stuff around, and that's the next thing that we choose in here. What's the next thing that we choose? Fascinating. Like, I don't really know. So we need to understand the sequence of events that happens. We are listening, right? Also, I would like to maybe, for the listening, say on which coroutine we are listening. So let's do coroutine ID. Let's just like print who's listening to what. So the 0th one is listening. That's cool. So then I'm connecting. So 1 is successfully connected. Then I'm sending some data there, and we received some of the bytes. So funnily enough, I can't connect the second one is connected, but if I try to send, I hate software. What the fuck changed? Oh, okay. All right. I mean, it's cool. So floating point, Heisenbugs again. But that's already progress. I wonder if we can reproduce that. Is this reproducible? Oh, now it is. Okay. Okay, so now we're. I don't know what was that. Okay, so can I now close this one? It is more or less reproducible, which is good. So it is more or less reproducible. So what is happening when 0 is returned? Right, so because it's supposed to close somewhere here, we do break outer and we return out of that. Maybe something with the stack. Maybe you need a bigger stack. So let's give you 20 megabytes of the stack, if that's what you want. You want like a big ass stack? We can give you a big ass stack. All right, so cool. Telnet. All right. So yeah. Maybe it's debug time. So, like, where exactly does it fail? We need to figure out where exactly it even fails. So let's rebuild everything. I might as well just rebuild it like that. Then gf2 build, what is that? Echo. All right, and let's just run it. I suppose we can just start doing things. It kind of blocked, I think. Is it working? All right, so can I close it? Okay, so, and it, aha, got you, motherfucker, got you. Aha, that makes it. The debugger was useful for the first time with the freaking, okay, I'm gonna say anything. So, alrighty. So that's what we're doing here. So we have to be careful with this kind of thing. Okay, so when you do finish, you have to repeat that whole thing. Damn, you really have to repeat that polling thing. Where can I find that Rolly polling thing? Switch context. All right, so this stuff before you can try to even do this kind of thing. Maybe we need to factor this thing out into a separate function, right? Because when you finish the routine, you may end up with 0 active coroutines, so you need to sleep here as well. So this is a candidate for factoring out into a separate function. Yes, I think that's the case. All right, so can we now try to run the whole thing? It is listening. Look at that. Telnet. It is okay. Telnet. Okay. And it is not spinning, it is actually sleeping, so I don't have a core. I think I don't have a core sleeping right now. Yeah. So we are accepting connections, but not a single core is sleeping. Or not spinning, that's what I meant. So, and we still can do things and then close the connections. I call it a win. And the cool thing is that this code looks very much synchronous. So let me show you. Where's the echo? Unlike the code with futures. So look at that. So you have a loop. Within the loop, you just accept things. You simply accept things, and then you create new coroutine, kind of lightweight thread. And within lightweight thread, you just sleep on the read, you read some stuff, and you write it back. Right, and the cool advantage over using threads in here is that you don't have to use synchronization between threads. Right, so you can have a lot of threads, maybe like thousands upon thousands of threads. I haven't tried that yet, but maybe we'll try to do that at some point. Maybe there will be some problem with the amount of memory because we have huge stacks now. I think it's 20 megabytes, like how huge was that? Yeah, 20 megabytes. But on top of that, we have a virtual memory, so it's not all of the 20 megabytes are going to be used. Right, so you can have a lot of connections in here, and if they all are sleeping, it's going to be totally fine. And then if you want to send information from one coroutine to another, you don't have to use mutexes, you don't have to use channels, you don't have to use anything. You can just have a global variable, right? So you don't have to synchronize all of these things because it's not multi-threaded program. It's a concurrent program, right? But it's not multi-threaded. And again, it's not going to give you speed up if you do a lot of like mathematical computations or anything like that. But if the only thing you do is just waiting on asynchronous I/O, this is actually kind of perfect. This is actually kind of cool, and it still stays relatively, what is it called? Relatively imperative, right? So relatively synchronous code. I really like that. That's actually super cool. So, and the coolest thing about that is that I fully understand how it works down to assembly. I used coroutines or coroutine-like things before, but they always felt like magic to me. They did in fact feel like magic, so I just like kind of accepted the way they work. But now I fully understand what is going on. Essentially, you have basically several states of the programs, and you switch between the states, and you store the states in a stack. You have several stacks, and it's not that hard. It is actually relatively easy. So yeah, and this is what I'm going to be using for my WebSockets library in C3 instead of futures. Right, so I have a WebSockets library. It is actually specs compliant, pretty much specs compliant. The only problem it has, it is synchronous. And throughout the like several months, I think I was exploring how can I make it asynchronous. I implemented futures in C3 because I'm coming from a functional background, so this is what I got used to. So it made sense to me that I want to use futures in here. I implemented futures and they worked fine, but to implement like asynchronous echo servers in future, I had to write this abomination, right? Just look at that. Right, so it's just like, it's such a weird code. Like, I don't freaking know. And now I had to rewrite my like imperative synchronous code to this weird style of futures with then and stuff like that, and I felt so demotivated. And then I discovered coroutines, and this is just like an imperative code. So I'm pretty sure I'll have to make a minimal modification to my WebSocket library and make it just asynchronous. And I think I'm gonna do that on the stream. So we're gonna have a separate session where I just like bring coroutines to WebSocket library, and hopefully with the minimal changes, make it asynchronous. We'll see how it goes. We'll see how it goes. But I don't think it's going to be difficult. Right, we'll see. And once we have a asynchronous WebSocket library, we can finally try to integrate it into server of Coil, right? So this game, online simple game, that many people think that is abandoned. In reality, it is not. So the last change was made. When was the last change? 3 months ago. So I was researching how to do asynchronous networking for 3 months. So I was on the verge of abandoning C3, right? So it was hard. It was hard. But I learned a lot. That was an insane journey, honestly. Holy shit. I learned so much about networking, about asynchronous programming, about all of this stuff. It's actually fucking insane. And I think my journey is finally over. And soon I'll be able to fully rewrite the server part of Coil in C3. So the server part of this game is going to be completely native. Client part, we'll see. I think I also want to at some point make it completely native. But in any case, I guess that's it for today. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you all on the next recreation programming session with Mr. Azozin. I love you all. Mwah.